Just look at the least significant bit for the index values. Okay, so that's how the sorting based approach works. Now, if you look at the other approach, it's little involved. What you have to do is you have to compute the parity value of your RGB cells. So you had it 0, 0, 0 and 0, 0, 1. So for this, you need to compute the parity value. This is your original image. So for the original image, compute the parity value, which is 255 plus 0 plus 0 mod 2 is 1. And you wanted to send a 1, 0. So the bit that you want to send is matching with the parity value for this index. So just send 0, 0, 0. Okay. Now for this one, compute the parity value. It comes out to be a 1. It does not match with the bit you want to send. So what you should do in the palette table, choose an index that has the same parity value as the bit you want to send. You want to send a 0, so look in the palette table. You are right now at this. So the closest index is either this or this. Okay? And you want to send a 0, right? Right. So what you should do, this one has 200 plus 0 plus 0 mod 2 is going to be 0.
0.
So you choose this. You cannot choose this. Why? Because 255 plus 0 plus 0 mod 2 is going to be 1. And you want to send a 0.
What if both of the closest ones is 0?
Okay, so if both are closest, so if you're this one and this one both are having the same parity value as you want to send, you have tie there. You can break the tie by choosing the lowest index value. In this case, for example, if you translate this to numbers, this is 1, 0, 1, 2, right? So you're at 1, you want to choose either between 0 or 2, so you would choose 0. Okay? So you can break the tie based on the integer values of those index values. Okay? Okay, so that is about images, how we hide information using these pixels. So now let's move on to how we embed in continuous signals that we generate when you want to send some audio or video signals. There is a technique called pulse code modulation. It has nothing to do with steganography as it is, but it is being used, or we can use this to embed information. So this is used if you want to send, in a networking class we would have gone through this, how to send a continuous signal from a sender to receiver, right? So if you are, say, all this voice over IP and all those stuff, or using something like this, it's called pulse code modulation. And a variation of it you see, which is called predictive coding, okay, after this. So what is the idea? You have a continuous signal that you are generating over time. Okay, so the signal strength is not discrete. If it is discrete, means what? The signal occupies only certain values, say plus 5 volts, 10 volts, and so on. Here it is a continuous function, something like this. So I want to send this information to the receiver, so the receiver can get back this signal. Okay? So, you know this is continuous. So how many integers are between, how many values are between 0 and 1? Infinity, right? You cannot count how many are between 0 to 1. So which means, again, in the signal, if you want to sample it out, we can really have infinite number of samples. So what you do is you discretize it by fixing, doing some time slots. So at this time slot, what is the signal values, right? So these are the values you are going to send. Okay? So you are going to refer this as integers 0, 1, 2, 3, 4, 5, 6 and so on. So typically we use multiples of exponents of 2. So either this is say 8 levels, or 16 levels, or 32 levels, and things like that. Okay. So of course, now what happens, as I show in this picture, you may encounter something like 2.5, which you cannot say, but you cannot send 2.5 because all your signals are discrete signal strengths, either or integer signal strengths, either 0, 1, 2, or 3, like that. So what we have to do? We have to do some rounding here. So we typically round it to the next closest integer. So this one could be rounded to a 3, and this could also be a 3, this is a 6, 4, and so on. So when I sample this continuous signal, I end up actually sending these points, 0, 3, 3, 6, these points. So when the receiver gets it, it has to use only those samples to construct back the signals. So of course it won't exactly match, there will be some kind of difference. Okay? So how accurate receiver is able to get back the original signal depends on the sampling. So if you use very small time period for your samples, you will have more samples, right? So with more samples, you will be able to accurately get back your signal. If you want to minimize the number of samples you are using, you won't be able to accurately get back your signal. Okay, so that's the idea. So there's a trade-off. If you use more samples, you have to send more bits, right? Why? Each of the sample signals levels are sent in terms of the or integer values, right? So you need to represent this in integer binary. So if you use 0 to 7, you can use just 3 bits. So if I want to send like this, say the origin is 0, so as assume the first point we'll be sending is 3, which is 0, 1, 1. The next point is also 3, so 0, 1, 1. The next point is 6, which is 1, 1, 0 in binary. Okay? So it is 3 bits, use 3 bits to send your integer values. So if you use more samples, then you will have to have that many integer numbers, right? So you need more bits per sample. So that's a trade-off. Okay? So that's the idea of pulse code modulation. And a small variation of it is called predictive coding. So here, the drawback with pulse code modulation is, as I said, if you increase the number of samples, you need more bits per sample. So to kind of reduce that to a certain extent, to minimize the impact of that, you don't send the absolute signal value. So previously we were sending this 3, 3, 6, and so on, right? Whatever these different levels are. So here we are not going to send the absolute values, we are going to send only what's called the relative difference, okay, between the samples. So for example, this point it is 0, this point we know it is 2.5 as I written here, this point is 2.9, this is 6.4, and this is 4.0, this is 1.8, and this is 1.0. So how do I capture this point? This point is going to be the difference between this level and the previous level. So that is 2.5 minus 0. So that is 2.5, right? We'll come back to this rounding business, or I can tell you that. So instead of sending 2.5, you round it to the next largest integer, which is 3. Okay, which is plus 3, of course. Why? Because we may get some negative values. The way you are doing this difference is the current sample minus the previous sample strength. So that's why it's 2.5 minus 0. Whereas here it will be 2.9, the current sample minus the previous sample is 2.5. So that comes out to be 0.4. So 0.4 is not greater than 0.5, so you have to truncate to a 0. Right? So which means if I send it, I would send this to be at 3, and the next value I'll be sending is 0. So what does it mean? The next signal, the next sample is the same thing. It's also at 3 because it's not changing. It's 0. That's the relative difference. It's represented using the delta sign. Now, this is 6.4 minus 2.9. So what is that? 3.5. Right? So 3.5, you round it is 4. So that's going to be 4 more than this. So this is going to be some 7. So if you really send this, it's going to be 7. Okay? Then this is going to be 4.0 minus 6.4. So now you start getting negative numbers because the signal strength is decreasing. So 4 minus 6.4 is negative 2.4. So negative 2.4, you round it, it is negative 2. So which means the next signal is going to be 5. Signal strength is going to be 7 minus 2, which is 5. Then the next one is 1.8 minus 4, which is negative 2.2. Again, if you round it, it's negative 2. So the next signal is going to be some 3. And then it is 1 minus 1.8, which is negative 0.8, which is negative 1. So that's going to be some 2. So that's how you get back your signal. Okay? So this is called predictive coding. Hmm? 3 plus this 4, 3.5 rounded to 4. 6.4 minus 2.9 is 3.5, rounded it's 4, so it's 3 plus 4 is 7. Okay? So, in the previous case, pulse code modulation, we were sending absolute values like 3, maybe another 3, 7, then 5 and all those values, right? So here what we will be sending? We will be sending only this delta values. What are the delta values? This plus 3, 0, plus 4, negative 2, negative 1 and all these things. So you work with smaller integers. You don't need to represent larger integers in binary. So if you want to represent smaller integers in binary, you need only few bits. Compared to representing larger integers like 10, 15, 20, that many samples, that will require more bits. Right? So that's the idea. Okay? Of course, its accuracy, as you see here, is not as good as the previous one. So, I don't show it here, so you can see like this. Compare this with the pulse code modulation, it may not be that accurate. Okay? But it saves you against a trade-off. It can save you some number of bits that you're using. Okay? Clear? That's called predictive coding. So again, we have not yet looked at how to use this for steganography. So this is just a background of pulse code modulation and predictive coding. So now let's see how we embed the data or do steganography with this predictive coding. Okay. So for that, the sender and receiver have to agree on a table that maps those delta values that you get. So we have to have a range of delta values, the difference in the signal strength for the current sample, the previous sample. So all these different possible delta values, negative 4, negative 3, negative 2 and all those stuff. Okay? So this mapping is something arbitrarily agreed between the sender and the receiver. So negative 4 is represented using bit 0 or something like this mapping. Negative 4 is mapped to 0, negative 3 is 1, negative 2 is 0 and so on. So you will be given this table. Okay? So given this and a sequence of bits that you want to send, okay? So given the steganography stereokeep table, and you wanted to send a sequence of bits, which is, say, this. Okay, I'll give you this, as well as the signal. So I haven't posted the sample questions for this yet, but I'll give you a figure like this with all the values. Okay, so you have to look at the image and compute what are the sample values, and so it's just interpreting the image. Okay, so I'll give you an image like this. You have to identify these signal strength at those points, okay, and compute the delta values. Okay, so let's say I give you this image, and I'll give you what the table as well as the message you want to send. So given these three things, the image like this or the signal like this, and the Stego key table and the information you want to send, right? So let's see how you hide this information inside that signal. Okay? So from what we just now did, this is what we did, right? We got this delta values for that signal, +3, 0, +4, if you remember these numbers, we just did this. So we need to use this information along with the Stego key table and the information you want to really send, and send what? Not this. If you send this, this is the original signal. So you want to kind of embed this into this, right? And send some modified values or different values, okay? Such that the receiver is able to get it back, construct the signal back, and also retrieve the information. Okay, so let's see how to do this. So the idea is, so let's say you want to send this bit 1, so each delta value will be used for a bit. So the first bit will be sent using this delta value, the second bit using this delta value, and the third with this, and so on. Okay? So you want to send bit 1 with this delta value, which is +3. So look in the table and see what +3 is mapped to. +3 is mapped to actually a 0. Alright? So it means you cannot use +3 to send bit 1, because +3 can be used to send only bit 0. So the receiver looks at the retrieved what it receives. If it sees a delta value of +3, it will understand it's getting bit 0. So you don't want the receiver to think like that. So you want to make the receiver think it's receiving bit 1. So what you should do, look in the neighborhood again. So you can increase by ±1, as I say. If it doesn't match like what we have situation, we have 3 +3 mapped to a 0, and we want to send bit 1. Right, so look in the neighborhood of +3, which is either +2 or +4, so ±1. So whichever thing is mapped to what you want to send, use that delta value. So here we see what? +4 is mapped to a 1, right? So we, instead of sending +3, we will be sending +4 for bit 1, okay? You also, in order to maintain what is called the uniformity of a signal, you see here, in order to find a suitable delta value, we move to the right, right? So the next time, if there is a tie that you could break, okay, you prefer to move to the left, okay, because we moved once to the right. Next time, if we have a tie, you prefer to go to the left. We'll see when that happens. Okay. So the next bit you want to send is a 1, and you have the delta value of 0. Delta value of 0 is mapped already to a 1, so you don't need to change anything, just send 0 as it is. Okay. Then you want to send 0, delta value is +4, so +4 is this now. And notice that you want to send 0, it's mapped to a 1. So you have only one choice here. You have to look to the left, because if you think you can wrap around, it's not really good, because the wrap around value is -4. So instead of sending +4, we'll be sending something -4. That's not good. So you have to just go to the left and see it is a 0, right? So it matches with what you wanted to send. So send +3 for bit 0. Okay? Then bit 1, you have delta value of -2. -2 is mapped to a 0. So now, as I said, we have a tie. It doesn't match directly. You wanted to send a 1 and -2 is mapped to a 0, right? So we have to look in the neighborhood. The neighborhood, you have two choices. You can either go for -1 or -3, right? Because both are mapped to a 1. Okay? So which one you will choose? That's where you will kind of break the tie depending on what you did before when you had a similar situation of looking in the neighborhood. When did we look in the neighborhood? When you wanted to send this for the first one, right? For the first one, we chose what? +3 to +4, and we moved to the right. So now we will try to move to the left. Okay?
I thought you only break a tie when you used that before.
Oh, yeah, we moved to the left from 4 to 3, right?
Okay.
Right, so we moved, for this, we moved to the left, right? So now we want to maintain uniformity, so we move to the right. Okay, we already moved left, right once, so now we again move to the right, so -1. Okay? Now we want to send bit 0, this is -2. -2 is already mapped to a 0, so 0 and 0 matches, so just send as it is. Then the last bit is 1, you want to send using -1. -1 is mapped to a 1 and 1 matches. You want to send a 1, -1 is already mapped to a 1, so there's no change loop in the neighborhood.
So you can use twice.
Huh?
You can use it twice.
Use what twice?
Like for example, if like -1, -1.
Oh yeah, for different bits, yes. So let me go over it one more time. So what will be given to you? That signal. So from the signal you have to generate this delta values by looking at the different samples, generate the different sample values, and then I'll give the stego key table as well as what? The information. So this is the key thing. So the message you want to really hide. So we'll use each delta value for a bit. So you want to send bit 1, you look at the delta value which is +3 and the table says +3 is mapped to a 0. So you cannot just use +3 because it's mapped to 0. So what you should do, look in the neighborhood. So you have only one choice, move to the right and choose +4 because +4 is mapped to a 1. Right? So that's why you're sending +4, 1. Okay? And then the second bit you want to send is a 1 using this delta value of 0. And the table says 0 is mapped to a 1. So you can send as it is, 1 and 1 matches. Okay? The third bit you want to send is a 0 with the delta value of +4. +4 is mapped to a 1 and you wanted to send a 0. So what you should do, look in the neighborhood and you have only one choice, go to the left. Right? So even if you can, if the previous time you move to the left and ideally you should move to the right and you don't have a choice here, just move to the left. You cannot do anything. Okay? So just move to the left and you will have 3 mapped to 0. If this 3 is also a 1, keep moving to the left and find the closest one you can have. Okay? So then what you have now, 1 using -2. -2 is mapped to a 0. So you have to look in the neighborhood, so either this or this. So you just move to the left, so you better move to the right now and say -1 into 1.
What if you move in either direction?
Then you prefer the right. If you read the description, I would have said preference will be given, the plus will be given preference or minus. So plus means it's increasing value, -2, -1, 0, 1, 2, 3, 4. So move to the right, preferably. Okay? Then you want to send 0 using -2. -2 is mapped to a 0, so you don't need to change it. Then similarly, -1 is mapped to 1, and 1 is what you want to send, so send it as it is. So last 2 bits is sent as it is. Right? So when the receiver gets it, what will happen? Receiver will reconstruct the signal, right? So this is what it will get. So this blue line is the original signal. The lower one is the signal before embedding. The top one is a signal after embedding. As you see, you are supposed to send 3, but you have sent 4 because of the embedding process. Then similarly, you send 0, you are supposed to send 0, you are also sending 0, but this 0 is 4 plus 0. So that's why you maintain at 4. Right? That's how you reconstruct the signal. Okay? Then 0 plus 3, which is 7, right? So 4 plus 3 is 7, right? So the previous case before embedding, you would have done, this is at 3 plus 4 is 7, but you see both are, it should be the same point. So this is plus 3 at 7. And then you are doing a -2 here, so from the original signal would be decremented from 7 to 5. as this signal is going to be decremented from 7 to 6. Okay? So you can see that the embedded signal is not exactly the same as the signal you would have sent without any embedding. But you should not make it look very different. If you make it look very different, it's going to be very obvious that you're embedding some information. Okay? So that's the idea. Right? Any question? It looks some little, what you call, micromanaging. You look at the image and then do this. Okay? So now let's move on to the last technique, which I don't think we'll have time, but let's see what we can do. This context-free grammar in programming languages, probably. Right? Okay, so here we have a sequence of a set of variables, a set of symbols, and some production rules, and a starting symbol. Okay, so I'm not going to the theory behind this. So let's say this is a grammar given to you, and these are the production rules, like for these different variables, S, A, B, C. You can have Alice B, Bob B, and so on. The idea is this: in the previous techniques that we have seen, all this, whatever you have seen before this, right? We had a cover, like the signal, or voice signal, audio signal, or an image, or whatever, and we hide our small sequence of bits inside the cover, right? And we send it. That's what we did. The receiver was able to extract back the hidden information. Here, what we are going to do is, we don't have a cover. We are going to generate a cover based on the message you want to send, right? So that's the key difference. The previous approaches, we had a cover, right? And we hide our small information bits inside that cover and send it. And the receiver was able to extract back the hidden information from the cover, right? But here, there's no need to send anything as a cover without embedding, because in the sense that the cover is generated because of the message or due to the message. Okay, so the nature of the cover that you will be sending is actually based on the message. Okay, so what is the message you will be sending is actually driven by the sequence of bits you want to send. Okay, so let's do an example that may make it more clear. So I'll give you the production rules for the context-free grammar. Okay, and so this is just for practice if you are not yet familiar with context-free. For example, if I want to derive the sentence "I am lazy," you start from where? The start symbol is S. So look at that S. Pick a production rule that starts with I. So it doesn't start with I, doesn't start with I, doesn't start with I. So this starts with I. So I and then A. So A, then again it needs to be am lazy. So it needs to be this one. So the derivation is S to IA, then A is I am lazy. So that's how you derive the actual sentence. Okay? So if you take that course, you will probably know more about this. So what we are interested here is, you might have seen Hoffman tree again in some previous work, but we'll construct the Hoffman tree with thing now. So I'll give you the production rules with some frequency of appearance of the symbols. So the first variable is 0.15, the next is 0.3, this is 0.5 and 0.5. So that is equivalent to this A, B and C appearing with this frequency. Okay? So each one has a frequency. Okay? So we need to be able to construct what is called a Hoffman tree for each of these symbols. Have you seen Hoffman tree before? Right? So it is to generate binary code depending on the frequency of appearance of the different combinations. So let's do it for S. So S, the different frequencies are 0.5, for Alice B, 0.3 for Bob B, 0.1 for Eve B, and 0.1 for IA. So what you should do is, originally you should write them in increasing order. So, or I have like that here. So 0.1 A, 0.1 Eve B, right? So it doesn't matter how you break the tie, you can have either three. Okay? And then 0.3 B, 0.5 this. So these four are in sorted order. So that's your basic requirement. So you should write all your frequencies in sorted order. So you're going for S now. Okay? So then combine the two smaller ones. Right? So the two smaller ones combine, 0.1 plus 0.1 is 0.2. So now see if this is in the same sorted order. So this is from left to right, 0.2, 0.3, 0.5. If not in the sorted order, you have to move something towards the left or rearrange so that from 4 nodes we are now reducing to 3 nodes. So these 3 should be in sorted order. So this is already in sorted order. Later we see a situation where things are not in sorted order, we have to move around. Okay? So now combine the next smallest two. The next two smallest values are 0.2 and 0.3. So if you combine them, that will make it 0.5. So now you have 0.5 and 0.5. So you can combine them and make it a 1.3. So finally everything should add up to 1. Okay? So now,
What is the meaning by between the nodes, there's a 0 or 1?
that's what I'm going to tell now. So what you want to do is, you want to represent these leaf nodes, these different rules using a binary code. And you want to use fewer binary code for the rule that appears more frequently. So now between these 4, this is the rule that appears more frequently, 0.5 to 50% of the time. So you want to represent this using fewer bits. Whereas the rule that appears very less frequently will be represented using fewer bits. Half-man code, if you know the theory behind it, is used for what? Compression. Okay.